Today I thought it would be a good idea to look at a couple of examples together, and that way I can point out some things about how a problem is worded and how we can put what we learned the past 2 days together and really dive into these polynomial functions. Now the directions for each of these problems, they're a little bit vague in some senses because there are going to be multiple answers. Actually, there's an infinitely many number of answers we could have depending on what the problem says. I'll talk about that a little bit, but for the most part, I'm going to write out the most basic polynomial functions given the constraints that we have in each problem, and then I'll talk about how you could have multiple answers and what would change and what wouldn't change. So number one here says write an equation of a polynomial function that has 4, 0, negative 5, 0, positive 5, 0, and 0, 0. The leading coefficient is negative, and we're going to identify the end behavior. So I'm going to have y equals, and we know the negative leading coefficient must be negative. So let's write that down. Negative, it can be any negative number. Let's go negative 4. Now the zeros. You could write them first or you could plot them first. It doesn't matter. I like to go through each one and say, okay, x minus 4, then x plus 5, x minus 5, and the last one, x minus 0. And we'll talk about what that means in a minute because we don't need to write minus 0. So the graph, if we look over here, we have a 0 at positive 4. We have a 0 at negative 5. We have a 0 at positive 5. And a 0 at x equals 0. So then when we graph this, because our leading coefficient's negative, the right side is going to go down, and we just draw our graph. Don't worry about, how did you know to go up that high over there or down this low over here? I'm more concerned about your behavior at your x-intercepts. Now you may be saying, well, how do you know that we're going to bounce or cross at these x-intercepts? And this is one of those instances where the problem doesn't say that. The original directions up here don't talk about the behavior at those zeros. So you could have a lot of different answers here, but this is the most basic correct answer. We're going to simplify this equation, because the x minus 0 we're just going to bring out here and not have minus 0 with it. So we have x minus 4, x plus 5, x minus 5. And then both of our n's are going down, so as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity as well. Then number 2 down here, it says write an equation of a polynomial with x-intercepts at 3, 0 and negative 7, 0. And then we have this end behavior. Okay? Because both sides are going down, this tells us two things. This tells us we have both ends going down. What this tells us is that your degree is even and your leading coefficient is negative. So the most basic graph would look something like this, a parabola open downwards. So we have y equals, and the leading coefficient could be any negative number, negative 7. X minus 3 times x plus 7. And you could have any odd number for your exponents. You could have 5 up here. This would still give us an even degree function because 5 plus the invisible 1 would be 6. So again, there are multiple right answers as long as your leading coefficient is negative and your factors have both, or your factors both are odd degreed. All right, let's look at number 3. Write an equation of a polynomial that could have a maximum of 5 turning points. So remember, if there's a maximum of 5 turning points, that means it has to be a degree 6. And the easiest way to write a 6-degree function is to have 6 x-intercepts. So I'm going to go over to my graph and just plot 6 random x-intercepts. And there is nothing in this problem about your leading coefficient or any end behavior. So we could have our functions go up or down on the right side. Whenever we go down, and then a graph, I'm just going to meander it through. So just to verify, we have 1, 2, 3, 4, 5 turning points. So now let's write the equation of this graph. Y equals, and we had a negative leading coefficient because I chose to start this function going down. It doesn't matter. You could have had a positive leading coefficient. This is just how I chose to do it. And then we have x plus 6 for our first 0 here. Our next one is going to be x plus 4. And then we're going to have x plus 1. And then we're going to have x minus 2. And then x minus 4. And then we're going to have x minus 7. So again, there were a lot of ways that you could have done this problem. This is just one of your correct answers. Number 4 says write an equation of a polynomial with a double root at 6. So double root, this means a multiplicity of 2. And again, it doesn't tell us anything else, so we have a lot of freedom here. The only thing we have to have is x minus 6, because plugging in x equals 6 into that factor will give us 0. So this is the only factor we have to have, and our exponent must be 2 because it says double root. So we can just leave this alone like that and be done with it. And your graph would start at 6, 0 and open upwards. Number 5 says write an equation of a polynomial whose degree is 4, has 3 distinct real roots. Okay, so degree 4 and 3 distinct roots. So what that 3 distinct roots means is that I have to have 3 sets of parentheses. So let's just make up x minus 1, x plus 2, and do x plus 6. So those are my 3 distinct roots, but to get a degree 4, one of these has to be raised to the second power, and that is because when we add up 2 plus this invisible 1 plus the invisible 1, that will give us 4. So this is a degree 4 function with 3 distinct roots. So let's graph this so we can get an idea of how many turning points there are. So I'm going to plot my zeros at 1, 0, negative 2, 0, and negative 6, 0. My leading coefficient is positive. I didn't change anything. I didn't put anything out there. The problem didn't say I had to. So because the leading coefficient is positive, the right side is going to go up. Now, the behavior at this 0, let's look at our equation. That even multiplicity means we're going to bounce here and cross and cross. So we must bounce at this 0. Now, you may be asking, how did you know, or why did you put x minus 1 squared? It didn't matter. I could have put that second power here instead of over here. My graph would look different, but you could have done that. So I think one of the things that most students struggle through with this is that there's no one correct way to do these problems. Number of turning points. We have one turning point, another turning point, and then another turning point. So we have 3 turning points. You remember, turning points are where the function changes. So like if we're going down and then going up, that's a turning point, or going up and then going down, that's another turning point. So don't get alarmed if there's not some information given to you. You just have a little bit of freedom. Here, I could have had a negative leading coefficient, and that would have changed the graph, but I would still be following the directions that were provided to me in this question. So that's just something that you'll get better at, taking what they give you and then just kind of filling in the rest with whatever you want. Number 6, write the following polynomial in standard form. So we're going to multiply this out using our box. We have x minus 1, x minus 2. So x times x is x squared. X times negative 1 is negative 1x, or just negative x. X times negative 2 is negative 2x. And negative 2 times negative 1 is positive 2. So my standard form would be y equals x squared. And we have negative x minus 2x, so it's minus 3x plus 2. So now that we're in standard form, finding these answers might be a little bit easier. The degree. When the equation is in standard form, the degree is only the largest exponent, so it's 2. You're not going to add 2 plus this invisible 1 and say this is a third degree function. You only do that when it's in factored form. If we look up here at the original factored form, those are invisible first powers there, and 1 plus 1 is 2. Leading coefficient, the invisible 1 in front, and then end behavior. As x approaches negative infinity, so the left side, because our degree is even and our leading coefficient's positive, both ends are going to go up. So y approaches infinity. And as x approaches positive infinity, y approaches positive infinity. All right, then number 7, write a possible equation for the polynomial below. So again, we're looking at this and saying we have an x-intercept there, and there. And the right side's going down, so I know my leading coefficient must be negative. So y equals, I'm just going to put a negative sign and not waste my time with a number. So negative x plus 2, because that's for this 0. We're not going to write x minus 0, we can just write x and x minus 1. And again, you could have any of these factors raised to an odd power because our function is, or our graph is crossing the x-intercepts. Our graph goes through each x-intercept. Well, how many x-intercepts do we have? It's 3. And how many turning points? Let's look. 1, 2. Whoops. So again, multiple correct answers for this one. Here, write a possible equation for the polynomial below. So this one is a little bit different because I see I have two bounces here at -5 and at +2. My leading coefficient is still going to be negative since the right side goes down. So I equals negative. And before I go and deal with the exponents or the multiplicity, I'm just going to write out the zeros first, or the intercepts. So this one is x plus 5. Here will be x plus 1. And here will be x minus 2. And the 0 at -5, so the x plus 5, that must have an even multiplicity. So we can put any even number as the exponent. We can put 4. Here, x equals +2. The factor that goes with that is x minus 2. I could have any positive multiplicity, any even multiplicity there as well, and it would be okay. Number of x-intercepts, we have 3 of them. And number of turning points, let's count. 1, 2, 3, 4. We have 4 turning points. So we haven't had this situation a lot where there are more turning points than there are x-intercepts. And that would happen when you have a lot of your x-intercepts also be considered turning points. 2 of our x-intercepts here are also turning points. So that's why the number of turning points is larger than the number of x-intercepts. We are not going to do this last problem. It's too much. So I hope that this clarified some things and helped you put everything that we've been doing together. I know that it is frustrating at times that there's no one correct answer. You could have had infinitely many answers for all of these questions and still been correct. So if you're ever confused, just ask me. But realize that just because I have one answer doesn't mean you have to have that same answer as well. So thanks for watching. Make sure you like this video and subscribe.